Okay, so this is going to be pre-calc 7.4 day 1, never gets changed over for whatever reason. Um, so after today's lesson, we will be able to write decomposition factors, decompose a fraction with distinct linear factors, decompose a fraction with a repeated linear factor, decompose a fraction with an irreducible quadratic factor, and decompose a fraction with a repeated irreducible quadratic factor. And then after that, we're going to apply our knowledge of key decompositions of partial fractions to fractions when graphing. Okay, so here's the deal. A polynomial with real coefficients might be factored into a product of factors with real coefficients where each factor is either linear or an irreducible quadratic factor. So recall from chapter P, u cubed minus v cubed has a pattern u minus v, the quantity times u squared plus uv plus v squared. So we can factor x cubed minus 64 to be x minus 4 and x squared plus 4x plus 16, which is the irreducible quadratic factor. And this section will show that a rational function can be expressed as a sum of rational functions where each denominator is a power of a linear factor or a power of an irreducible quadratic factor. Each fraction in the sum is a partial fraction, and the sum of a partial fraction decomposition of the original rational function. So we got to kind of go through some of this to be able to kind of debrief it. But as we go through, I'm really talking about rewriting 3 over x minus 4 plus 2 over x plus 3 as a single rational expression. What we have is partial fractions here. I've already have the partial fractions, and we're going to find the single rational expression by first finding like denominators. In order to do that, I got to multiply 3 over x minus 4 both by x plus 3 over x plus 3. So this becomes x plus 3 over x minus 4 x plus 3. And then the other side, 2 over x plus 3, I got to multiply by x minus 4 over x minus 4 in order for me to combine the terms alike to have a like denominator all the time. Now, after I get these set up, let's pull these over so I have some room. I'm going to be able to combine the terms after I distribute. So I've got 3x plus 9. And maybe perhaps if I say that, I could write it at the same time, plus 2x minus 8. That's over x minus 4, x plus 3. Now, when I'm done, I combine like terms and I got 5x minus 1 all over x minus 4, x plus 3. So what I just did is took two partial fractions and combined it to a single rational expression. What we're learning how to do is to undo that. So we're going to take that single rational expression to find the individual partial fractions. And this is how it's going to be done. Okay, we need to go back to doing a fix here. There was a mistake made, and we are backing it up to fix that mistake. And it is a sign mistake, and it's right here. This should have been 5x plus 1. And this is 5x plus 1. Now at this point, after we set this up, in order to find our partial fractions that created our rational expression, we now have to multiply by x minus 4 times x plus 3 all the way across both. So this can be a x plus 3 plus b x minus 4. Now after we do that, we got to distribute. So I've got 5x plus 1 equals ax plus 3a plus bx minus 4b. Okay, now I'm going to combine like terms here. So I've got 5x plus 1 is equal to a plus b x, because they are my x terms. And then I've got my constant terms, which is plus 3a minus 4b. Now keep in mind, 3a minus 4b has got to equal to 1, and a plus b has got to equal 5. Now at this point, we got 3a minus 4b is equal to 1. Now if I multiply the top by 4 using linear combinations, now I get to go 4a plus 4b equal 20, and I have that equal to 3a minus 4b equal 1. And now I have a combination where 7a is equal to 21 and a is 3. And after I find out that a is 3, I can pop that back in, to find b, and b is 2. So now I know a is 3, b is 2, and I can go back up here and say, well, gosh, I now know by my partial fractions results that rational expression, 5x plus 1 divided by the quantity x minus 4 times x plus 3, is actually made up of, and remember, a was 3, x minus 4, plus b is 2, x plus 3. And that is our solution to this. So basically, that's what we're going to be doing in a nutshell. Okay, and let's try to go along and talk about the different things that we did. Number one, first, f was not bigger, 5x is not bigger than x minus 4 times x plus 3. So I did not have q of x. That was not in my partial fraction solution. Now, when I factor dx into a product of factors of the form mx plus n, or ax squared plus bx plus c, where ax squared plus bx plus c is irreducible, I didn't have an irreducibility issue. And I didn't have repetitive factors. I did have, however, when I did this, I had two separate factors that I had a on top and b on top for. After I do that, it's clear fractions, and I'm finding my a and b, so I can find my originals. And as we go over more difficult problems, we'll talk about the 1 area, the 2 area, and the 3 area, and why I do repetitives as we go. And one of the things I want to come down is notice that the denominator kind of tells me what I use for the numerator when I'm working with the partial fractions. Okay, the highest power of the denominator tells me that my numerator is going to be 1 less. So that's why I use constant terms and linear factors, constant terms on top, linear factors on the bottom on my example. But we will be working with just 1 less power on the top. And we'll talk about that as we make connections here. Our first thing is writing the decomposition factors, right? The terms of the partial fraction decomposition for the rational function. Now, when I have repetitive factors, I have to write it just as many times to represent that factor. So when I'm doing this, 5x minus 1 divided by x cubed, x plus 3, x squared plus 1 is going to be written, first of all, I'm going to pay attention to that x cubed part. The x cubed, I've got a over x. Now, that's only to the first power, plus b over x squared. That's still dealing with my x cubed. Okay, now I've got to write c over x cubed. Now, I've taken care of the repetitive nature of that factor. And the next thing I'm dealing with x plus 3. Okay, and again, another linear factor. So I just have a constant on top, and I only do it once because it's not squared, cubed, or to the fourth or whatever. It's just the first power. And now I have a irreducible quadratic factor to deal with. When I do that, I recall the fact that my power on my numerator has to be 1 less than the power in the denominator. Since it's x squared, it's a quadratic. The denominator has a quadratic, the numerator has to have a linear factor, and my linear factor takes the shape of, gosh, it should be here. Maybe we can get it to reveal itself. And it's gone. I fixed it and it's gone. So we're going to get it to reveal itself. Should be EX plus F. Okay, it should be a linear factor on top if I have a quadratic on the bottom. And that's how I do the setup, and I'm not of my decomposition. And I am not solving that. I was just asked to write the terms for the partial fractions decomposition of a rational function, but do not solve for the corresponding constants. So everything's set up, but I'm not solving this one. Okay, let's look at number 2. I'm going to solve that. So I've got to factor the bottom, x minus 3, excuse me, x, it looks like an x minus 5 and x plus 3. And on the top, I have 5x minus 1. Now remember, when I get this done, I am going to be looking for an answer because I'm going to set up a over x minus 5 plus b over x plus 3. And this is that 5x minus 1 over x minus 5, x plus 3. The hardest part of this is the setup. Okay, once I set this up, my next step is algebra. And my first step is to clear the fractions. So I'm going to multiply both sides by x minus 5 times x plus 3. And now after I get that done, after I get the clearing of the fractions done, I got to distribute the a and the b to the x plus 3 and the b, x minus 5. So I got 5x minus 1 equal ax plus 3a plus bx minus 5a. Now I've got to combine like terms, and so I get my a's together. I'm going to do this color-coded wise, and I've got a plus b times x, and then I've got 3a minus 5b. That should be a b. 5b. Sorry about that. That should be a b. Let's make that change. Okay. And now, as I'm looking it over, okay, I still have 5x minus 1. Keep in mind, we just did systems of equations, and I'm setting up a system. I've got a, let's stay with our color coordination here. I've got a plus b is equal to 5. That's my x. And I got 3a minus 5b equal to negative 1. Now, in order for me to get this done, I have a choice to put it in my calculator as a augmented matrix or an inverse matrix and make the solve. Or I could just do systems of equations and multiply the top equation by 5 to get rid of the b values. So I got 5a plus 5b equal 25. Okay, so I'm going that way, and I've got 3a, because that's not going to change, I'm just going to show it the same, minus 5b equal negative 1. Now I'm going to combine like terms, and I've got 8a is equal to 24, so a is 3. Now I take my value for 3, pop it back in, I find out that b is 2, and since a is 3, b is 2, I now can write the solution to a is 3, x minus 5, and b is 2, x plus 3, and that's my solution to my system, where I've got a and b answers. And probably more correctly, I should probably get rid of the e's and say it this way. So this is my solution as I go. Okay, so I've got that linear system solution, but let's talk about what might happen if, if I use my calculator to do my solving using the inverse matrix. I can do it that way, but let's talk about supporting my solution graphically. As I do this solution graphically, you got to be aware that, and if I've got it here, and we are going to clear this second clear, actually we're going to clear this, y equals, okay, I'm going to put the solution in my calculator because I want you to see how the partial fractions affect our graph. Our original rational functions on top, and then the two partial fraction values that we found is in y2 and y3. If I graph this in a square standard graph, I get the original, which is my blue. My blue is the function itself, and the partials are the yellow and the red. Okay, the yellow and the red combined to be that first one. The yellow and the red combined to be this one. Did you notice that the red comes through and supports it, and the yellow comes from the top and comes out? And now the last one, the red kind of comes down and it supports that. So the blue that's there is the actual function, and the yellow and the red are the impact shown by our partial fraction that we found that make that rational function. Okay, and we'll do more of these tomorrow on notes, and we'll have some problems to actually, determine which function was created by which partial fractions. Okay, as we're going on to this next one, and remember that's what we did. I just did that over on the calculator so you can see what I was doing there. So remember the fractions, the function that is created was this one, x squared minus 2x minus 15. And the partial fraction that was found where a was 3, x minus 5, and b 2, x plus 3. So that's what we graphed, so we were able to see what was going on there. Going on to our next problem. For number 3, we are going to decompose a fraction with repeated linear factors. So now, this decomposition, keep in mind, I'm really concerned about the denominator. So I'm going to factor out an x, and that gives me x squared minus 4x plus 4, which is really x minus 2 quantity squared. So I have a repeated linear factor here. And how I'm going to deal with this is I have ax plus b x minus 2 plus c x minus 2. And remember, the repeated factor is gone through until I get to its square. This is squared, so that's squared. If it was cubed, I would do one more term. Okay, now, just like we did before, we multiply across to be able to clear out our fractions. So my next step, I got negative x squared plus 2x plus 4, and I've got a times x minus 2 quantity squared plus b times x minus 2 plus c times x. Now, just like before, I got to distribute. So again, negative x squared plus 2x plus 4 is equal to ax squared minus 4ax plus 4a plus bx squared minus 2bx plus cx. Oh, that was nice. Now I'm going to combine like terms. So my ax squared, my bx squared, and my negative x squared. Okay, keep in mind, but I'm getting ahead of myself. I'm not going to try to combine those right now. I want to make sure you see why I can combine them that way. So I've got a plus b x squared. Okay, and that's my black. Now my green, I've got my x's. So now I've got plus negative 4a minus 2b plus cx. And my last one is just cx. Oh, nope, I lied. My last one, I'm going to use blue. My last one is just 4a, plus 4a. So now that we've got that set up, keep in mind why we're here. I've got the black here, that's negative 1. So I've got a plus b equal negative 1. Now I've got the x's all equal 2. So I've got negative 4a minus 2b plus c equal 2. And my last, finally, 4a is equal to 4. Well, I'm going to do back substitution on this. I'm not going to put it in the calculator. You could, but it's easier for me to see that 4a equals 4, so a must be equal to 1. And now, since a is 1, a plus b is equal to negative 1. Since a is 1, b must therefore be negative 2. And since I know that b is negative 2 and a is 1, I can plug it into this one and find out c. So negative 4, negative 2 plus c equals 2. Now I'm going to find out by substitution here, a is 1, b is negative 2. So that's negative 4 and positive 4, that's going to be 0. So c is just 2. Okay, so I know that a is 1, b is negative 2, and c is 2. Now that a is 1, b is negative 2, c is 2, I've got to house my solution, and it's going to come back to the fact that now I know A is 1. Okay, so it's 1 over x plus b being negative 2 over x minus 2 plus c being positive 2 over x minus 2 quantity squared. So this is my solution in partial fractions to the original. Now we're going to skip the next page and we're going to go to example 4. It's our last one on day 1. And as I go to example 4, I want you to realize it's going to show how to find a partial fraction decomposition for a rational function whose denominator has an irreducible quadratic factor. Okay, so before we had linear factors and we used constants. Now we have quadratic factors and we're going to use linear relationship. So first let's factor it out, and we have a grouping factoring. If we can factor the denominator out using grouping skills, I see x squared, I'm going to group these two together and these two together, x squared times x minus 1 plus 1 times x minus 1 on the bottom. Okay, and I'm just going to do it this way slow so you can see what I'm doing. And now I've got x squared plus 4x plus 1, and I've got x squared plus 1 times x minus 1. So now I have a linear factor in an irreducible quadratic, as promised. And as we go through here, I'm just going to pull this stuff over. Perhaps I'll pull the whole thing over and set up our problem. So again, to set this up, I have my linear factor, and I'm going to put a with the linear factor. And I have an irreducible quadratic, so I need a linear on top. Bx plus c is a linear representation of the values b and c, you know, if I think about mx plus b form. And I have my quadratic, x squared plus 1, on the bottom. Now, once I get this set and I'm happy with how I'm set up, I'm just going to do exactly what I've been doing. I'm going to multiply by clearing the fractions. Excuse me. So x squared plus 4x plus 1 is equal to a times x squared plus 1 plus bx plus c times x minus 1. And now I'm going to just multiply those factors. So I have ax squared plus a plus bx squared minus bx plus cx minus c. So I just multiplied those out, and now I'm going to combine like terms. Okay, so I've got x squared plus 4x plus 1 is equal to, and my terms that are like my x squareds. So I've got a plus b x squared. I've got a, oh, excuse me, I got to go with my b's. Let's go with my x's only. So I got opposite of b, so plus opposite of b plus c, x, and then my last one, we'll use black, is a minus c. So I got plus a minus c. Now, the reason I did that is that's plus a minus c. This is my x squareds, and this is my 4. So as we're working through, I'm making that connection. And so now I know a plus b must therefore equal 1. Okay. Opposite of b plus c is equal to 4. And my last one, which is black, is a minus c is equal to 1. Now, I'm going to solve this in an augmented matrix, reduced row echelon form. I'm putting this in an augmented 1, 1, 0, 1, 0, negative 1, 1, 4, and 1, 0, negative 1, 1. So I'm going to put that in a reduced row echelon form. Okay, and my final answer here will shoot out in my calculator. I will have 1, 0, 0, 3, 0, 1, 0, negative 2, and 0, 0, 1, 2. for my solution here. So that means A is 3, B is -2, and C is 2. So when I write my solution on top, I will know that I will have an A of 3 over x minus 1 plus my B, which is -2, -2x plus 2, which is C, over x squared plus 1, which is equal to the original function all set up. So that's my solution to this decomposition. Now, here's the thing. Be careful about your algebra. Reread the steps that we would take to complete the problems, and we'll start again tomorrow and we'll talk about the order of things. I hope things are going well. If you got questions, please ask in class. Hope the videos are working for you. You guys have a great night.